This is Bart Kosko at the University of Southern California. What happens if you replace a variational autoencoder with a bidirectional one? We'll show that if you do it right, you reduce two networks to one, and in one stroke, cut roughly in half the number of tunable parameters. You also get, on the image test sets we look at, slightly better performance. The bidirectional structure encodes in the forward direction and decodes in the backward direction through the same set of parameters, through the same synapses. But you do have to train with a new algorithm. Quick review, what's an autoencoder? It's a simple way to approximate the identity map. So for example, to take your face as an input image, run it through the network, the encoder, the latent space, out to a decoder, and get your face at the output. You might want to compress it, you might want to vary it. If it were text, you might want to map a book to a summary of the book, a screenplay to a summary of the screenplay, and so forth. The encoder uses parameters phi in its network, the decoder theta, so it's an optimization over two parameter sets. In the old unidirectional autoencoder case, it looks something like this. Image comes in, noisy, encoder network to a latent variable or hidden variable space Z, usually just a vector. And then that maps through the decoder to the output. But in the bidirectional case, which we've recently extended, it's just forward encoding, backward decoding through the same set of synapses, run locally as a bidirectional associative memory. We use weights in the forward direction and weight transpose matrices in the backward direction. You can't just run the unidirectional network backwards because you'll get noise at the output. And that's because most folks are using the unidirectional backpropagation rather than what you need here, the bidirectional backpropagation algorithm, the fairly recent algorithm from 2016. Here's the site to 2019. So you have a probability in the forward direction, the likelihood, and more generally a posterior, in the backward direction, a likelihood, and you're optimizing the joint likelihoods forward and backwards. So here, forward direction, it's a multinomial probability to a classifier output, running that backwards to something like a Gaussian, and jointly optimized, and that gives you the advantage of tuning the weights, and it encodes all that information, the forward and backward information, in the same set of synapses. Why use a variational autoencoder at all, this Bayesian extension? Because it's more powerful than AE, even though it's more expensive in terms of design and computational costs. It doesn't just map to a vector Z, but rather to a family or mixture of prior probabilities on Z, usually normals. It's regularizing or penalizing this latent space with priors. So as an example, if we have MNIST digit data, the autoencoder gives okay images you see on the left, but not as good quality as you see on the right with the VAE. It also, on the right, has a lower negative log likelihood. The lower, the better. The unidirectional case has a problem, a bottleneck, and that involves a hidden posterior of the variable Z given the data X and the parameter theta. And that's because of the mixings of the priors. And that's because of its Bayesian structure, this ratio, where the denominator term in green is the encoder, the numerator is a decoder in blue times the prior over the hidden variable Z in the latent space. And that denominator expands and that Bayesian normalizer as a continuous mixture or compound, and that can be intractable, even if you use something like Monte Carlo to approximate it. Monte Carlo reduces the error, but slowly, roughly 1 over the square root of the number of samples. So to get one more decimal point of accuracy, you have to increase the number of data points by a factor of 100. At the heart of a VAE is the ELBO, or evidence lower bound. It arises through the EM trick of the expectation maximization algorithm. It allows you to take what you're interested in, the likelihood, the probability of X given theta, and write it in terms of any random variable Z, as long as the probabilities are positive. So you can pick that Z out of thin air, so to speak. It's latent or unobserved or hidden. And the trick is to take the ordinary definition of the hidden posterior Z, X theta here. And you see in the first term, which equals the ratio of the joint over the marginal, and swap the left side with the denominator. So that gives you, on the right term, after the if and only if, your likelihood now written in terms of Z. Take the logarithm of that, use conditional probabilities, take you to the second equality, multiply the numerator by 1, and depending on how you pick that numerator, you'll get different results here. Here, we're picking it to be the ratio of the hidden posteriors of the encoder network, so it depends on the green phi parameters. Expand that through the log of the products of some of the logs. We get a decoding term in red, encoding in blue, and a residual term. If I now average that over the hidden posterior, that doesn't affect the log PZ since it doesn't expressly depend upon Z. And then when I'm through with the calculation, if I write it in terms of the pseudo distance or the Kullback-Leibler divergence DKL, which is the integral of P log P over Q, when the smoke clears here, I have this term in first brackets, the expected value minus that pseudo distance. That's the evidence lower bound plus a residual pseudo distance term, which is always non-negative. So if I drop that, I get the elbow bound that you see below. So training a unidirectional VAE has to maximize that lower bound, very much like in the EM algorithm. And what's going on when you do that is you make the elbow bigger, you're in effect moving the posterior of Z given X phi, making it more like that of Z given X theta. In the bidirectional case, again, we're going to encode in the forward direction, decode in the backward direction, and I put a red subscript on the probability B here at the bottom to indicate that we're interpreting the way we're implementing that conditional probability is through the backward pass. That's how we'll bring in the directionality. And now we get a bidirectional elbow, let's call it BELBO. It's similar to before, but the difference now in the expansion, where I have the number 1, I replace it with the ratio of the hidden posterior Z given X theta. Expand all this through, and nowhere in the expansion, it goes through as before, does phi occur. The directionality comes in, again, because in the backward pass, I'm getting the decoding piece of B. So when I'm finished, I have the BELBO term. I want to maximize it, but there's no phi around. And you can see that here as well. So maximizing BELBO drops the need of using phi. I do have to use, again, the bidirectional backpropagation algorithm, but combining that with BELBO, we're good to go. So I've dropped that extra parameter. 3 test sets, Fashion MNIST, CIFAR 10, and Celebrity 64. And I'm going to compare that to convolutional networks and bidirectional versions of residual networks. Like something like this, with the residual has some skip connections. We are using NOVA non-vanishing, the new neurons that extend logistics so they don't have a vanishing gradient. And a little more generally, would perturb that both in an additive way and multiplicative called GNOVA. It outperforms both logistic and ReLU. And logistic dies faster than ReLU. GNOVA dies slower than all of those. In the Fashion case, what we see, you see in the yellow, Fashion MNIST, that we roughly cut in half the number of parameters, and all the performance measures go in the right direction. Negative log likelihood goes down the bidirectional case. For Shea, inception distance goes down, peak SNR goes up, structural similarity goes up, accuracy goes up, so forth. The same thing we see with CIFAR 10, same cut in half, same correct direction on the negative log likelihoods, the for Shea, the SNR, the structural similarity, and the accuracy, and also a Celebrity 64. A lot of potential benefits here, and they have the form of compressing and augmenting and doing different generational tasks with image models, large language models, and there'll be hardware speedups and reconfigurations because you're cutting those parameters in half. So in summary, bidirectional VAEs use bidirectional backpropagation and ELBO. The result is just one network. Bidirectional VAEs, everywhere that we tested, outperformed unidirectional VAEs and at no extra cost. And we reduced again the parameter size by 50%. Thank you.